I'm going to talk to you today about a topic that I get super excited about, and that is a machine learning based approach for faster and more precise rock type classification. And specifically, we're going to talk about Facimage, which is one of the tools within our formation evaluation toolkit. And it's specifically focused around machine learning, both cluster analysis as well as regression. Today, we're going to focus on the cluster analysis or facies classification in terms of the machine learning workflow and world. Just to give you an idea of where we're going to go today, I'm going to start off with an introduction to introduce the topic of Facimage. Here, what I like to do is really make sure we're all on the same page when we talk about terminology and things of that sort. And then I'm going to talk about the clustering methods that we have available within our Facimage tool within geolog before going through a workflow overview. And then for me, as always, I really prefer to show instead of tell. So we're going to go through a simple demonstration where I build a model for one well and propagate that out for multiple wells, and how we can use that and leverage that model to help us identify our best reservoir rocks. Okay, so then we'll wrap up with key takeaways. So that's what we're looking at today. As far as an introduction, let's talk a little bit about Facimage. It's a tool, when I first saw it early on in my career with Paradigm at the time, now Emerson, I thought it was something that was pretty neat, but I didn't quite understand what the full scope of it was, how it could really be utilized until I got more into my career. And when I started to use it and started to see how quickly and easily it would allow us to go through and classify our data or come up with different electrofacies or predict logs or things like that, I realized how powerful of a tool it was. So with Facimage, it is our tool that will basically take our log data and allow us to analyze that data on a statistical or neural network methods, so that we can either look at classification or regression, so where we can predict different classes or facies, or where we can predict logs through KNN or K nearest neighbor type workflows. We actually have 4 different clustering algorithms that are a part of Facimage, and we'll talk about those more in detail when we get to it. I've already touched on this a little bit, but we can use Facimage to predict properties like log properties. I think perhaps more importantly, predicting core properties, because obviously we only core certain parts of the well, and being able to extrapolate from those parts of the well to other parts of your well or to wells where you don't have core can be super valuable. We can also do something called similarity analysis, which allows us to decide or look at and evaluate whether the model that we have built is appropriate for new data that we might be gathering within our field. So these are the 3 main ways that we can leverage Facimage within geolog for characterizing and classifying and predicting classes, predicting properties, and similarity analysis. So we're going to primarily focus on electrofacies for this particular presentation. So I just want to make sure we're all on the same page with regards to what an electrofacies is. I think as geoscientists, we all know what a facies is. And basically what we're doing is looking at, we're adding that electro component to it because we're looking at and determining these facies based off of our log responses. So Sarah and Abbott in 1981 were probably some of the first people to use the term electrofacies, and Ryder sort of extrapolated from there. But basically what both of them were saying was that electrofacies are rock types or classes that are generated by looking at distinguishing differences in the log responses. Okay, so let me say that again. Electrofacies are facies or rock types or clusters or classes that are generated or distinguished by differences in log responses. Okay, I do this just to set us up so that we're all on the same page for the rest of the presentation. We're going to talk now about the different clustering methods that we have available within geolog, within the Facimage tool. I think those of you who've worked with machine learning algorithms outside of geolog with Python and things like that will know that there are a number of other machine learning techniques out there, like deep neural net, random forest testing, and things like that. I'm going to focus on what we have specifically in geolog, and that is multi-resolution graph-based clustering, dynamic clustering, ascendant hierarchical clustering or AHC, and self-organizing map or SOM. Now, of these 4 clustering techniques, dynamic clustering, AHC, and SOM, were all developed outside of the energy industry. They were developed in the neurosciences and biology and used primarily in fields with lots of data that you need to do quick and easy classification on those data sets. Multi-resolution graph-based clustering, however, was developed by people within the industry, specifically Philippe Rabelais and Xinjin Yi. And this was work that they had done when they were at ALF, and we're going to talk in detail about MRGC as we go forward. But I think the big takeaway here is that MRGC was developed by people within the industry to work on and work with geoscience data sets. And to me, that will become important as we talk about this in a little more detail. Now, with this slide, I asked what is the best method, and I know I've tipped my hand already. As I said, we're going to talk about MRGC in more detail, but there are reasons why my personal belief is that MRGC is perhaps a better method than self-organizing map, dynamic clustering, or ascendant hierarchical clustering. And for me, often when I work with clients, I don't come into their offices or work with them knowing as much about the fields or the field or fields they're working on. So I don't have that in-depth knowledge of the basin evolution or basin analysis that they might have. MRGC is great because I don't need that prior information, that prior background, or understand that data structure to be able to use MRGC and get some useful information out of it. The other part of it for me is as a scientist, I really like my data to speak for itself. I'm very much focused on what is the data actually telling us. I don't want to unduly bias the model because of my own preconceived conceptual model of what I think is going on. We've got a last line in there, fast against large data sets. With the way our computers are running these days, that's not as applicable here, but there was a time when this was actually quite important. I think the big thing for me is with self-organizing map, dynamic clustering, and ascendant hierarchical clustering, you have to know about your data before you actually progress. And what I mean by that is, with each of these, you are going to give a starting value. Basically, with dynamic clustering and ascendant hierarchical clustering, you're going to say, I want you to go out and find 5 facies or 8 facies. With self-organizing map, you're going to basically say, I'm looking at, maybe a 2x2 or 3x3, so that'll give you 4 or 9, or whatever your grid might be for that map. The thing to realize here, though, is that you have to make a call of how many facies you want the model to find, as opposed to letting the data speak for itself. Because of this, the results of these 3 techniques can be very sensitive to those initial conditions. MRGC is a little bit more robust in that all you're going to do is tell it, I want you to see if you can get to as few as, let's say, 3 facies. And I want you to see if you can get to as many as, let's say, 25 facies. And let's break that out into, say, 20 models. This will become clear when we get to the demo, but for me, what that allows me to do is really let the data kind of shine through. So without repeating myself too much, as you can see, I tend to lean towards MRGC. So what is MRGC? Well, at its core, it's really a dot pattern recognition method. It's based off of a K nearest neighbor approach, and specifically a non-parametric K nearest neighbor approach, as well as a graph representation. You can find out more about this looking at the paper by Xinjin Yi and Philippe Rabelais that's listed on the bottom, New Tool for Electrofacies Analysis, MRGC Multi-Resolution Graph-Based Clustering. That is the paper in which they go into the details of what MRGC is and how it works and how they came up with the algorithm for MRGC. What MRGC is going to do, I mentioned it's a dot pattern recognition method, but what it's going to do is it's going to look at the data, the input data. So if you're using 2 logs, it's going to look at those 2 logs and all of those data points and how all of those data points relate to each individual log and all of the individual points, but also the collective collection of the points. So basically, we're analyzing all of the data, and from that, what we're going to end up getting are natural groups of data that are formed And these different groups of data, they're going to be of different sizes, have different density of points. They're going to be separated. They're not going to have necessarily regular separation as you might find with something like SOM as a for instance. I think the big thing to keep in mind with this is that we're going to have clusters that are going to vary in size, which is what we actually would get in nature. I think everybody would probably agree that our facies, we're not going to get the same density of points for facies for a facies model. That just to me doesn't seem really geologically realistic. I guess it could happen, but there's a lot of variability in our subsurface data, and that's one of the things that you'll see from here. So I think the other thing that I want to sort of point out about one of the strengths of MRGC is because our classes, those groups or facies, are defined by all of the points that we put into the model. All of the points that are, part of, basically it's how all of those points relate to all of the other points. We're not relating those points to a synthetic point, to like a barycenter. By doing this, that means that we're going to fully honor all of the points in the model, which allows us to handle discrete data without any degradation. And that's one of the big points with this. When we do self-organizing map or ascendant hierarchical clustering or dynamic clustering, we end up smoothing the data a little bit. So how does this work? I'm going to keep things at a high level here. The paper that I mentioned on the previous slide actually goes into a little more detail. But there are two things that we derive when we run MRGC. One of the first things we get is a neighboring index, and this gives us an idea of the local data density. It's basically how does that point relate to its neighboring points. That's the neighboring index. We also get this kernel representative index, and you'll see there it says local motive probability function. Basically, it's how representative are each of the points to any of the clusters, to the main cluster that it might be in, but also other clusters around it. These two indices, that neighboring index and that KRI, the NI and the KRI, we use these to form small natural groups of data or clusters. And then we basically will combine these clusters to make coarser models. So that brings in one other component to MRGC. So it's not just the MRGC, but it's also this concept of coarse to fine self-organizing map that happens as part of that workflow, where we take these clusters and then we basically order them using that sort of structure. And that KRI is the key component to that. So the KRI has a value from 0 to 1, basically. And what we're looking for are breaks in that KRI. So you'll have here on the x-axis our KRI, and on the y-axis the number of the individual clusters. And so you'll see here we have a break between 2 and 3. So we'll have one model in this instance that would have 2 facies. Our next break happens between 5 and 6. So we would then have a model that would have 5 clusters. The next break happens between right around 8. So then we get a model that has 8 clusters. We could continue on. The next one would be about 12. The next one would be close to 20, and so on. And so what you end up getting is not just one model that has however many facies you've decided upon. You get multiple models that go from a coarse model with very few facies up to a very fine model with a lot of different facies, depending on what your minimum and maximum are that you define when you build the model. So the beautiful thing about this is you don't have to do this manually. MRGC automatically determines the optimal number of clusters. And what this allows and what this does is it gives geologists control over the level of detail they actually need. So if you're a lumper, you can look at the coarse models, or you can look at that very fine model and start merging clusters together to get the model that best suits your needs. If you're a splitter, you can look at those high resolution models, and maybe that gives you the resolution that you're looking for. So let's talk a little bit about the workflow. So generally, as with any type of modeling, the very first thing you want to do is define your objectives. Because in defining your objectives, that's going to help you determine what your input logs are going to be. Once you've done that, or hopefully before you've done that, you've already gone through and done quality control on your data. So in other words, getting rid of invalid data, identifying any bad hole conditions. If you need to do depth shifting or environmental corrections, those will have been done, and any type of normalization. You want to approach MRGC, or sorry, you want to approach any type of electrofacies modeling, not just MRGC, with a clean data set. The next thing you're going to want to do is make sure you know what your key well or wells are. And what you want to do with this is you want to make sure your key well or group of wells has data that runs from the top of your zone of interest to the bottom of your zone of interest. And it doesn't have to all come from one well. You can basically use multiple wells to make sure you've got a data set that covers your key zone of interest. Because what happens is we end up building this sort of pseudo well, and I'll talk about that when we get into the demo, that actually pulls together all of the data from the different wells and different intervals, and basically makes a composite well for us. Once you've done that, then it's time to generate your model, evaluate, and then select your preferred model, and then you actually will propagate that model to the rest of your wells, including your training wells. So defining the objectives, I think, needs a little more time spent on it, because when I'm working with clients, one of the things they always ask me is, how do you know what logs to use? And to me, this really depends on what you're trying to model. And for me, like if you're looking at mineralogy and porosity or even lithology, I would really start off with things like density, neutron. Really, I would probably use neutron density separation instead of neutron to remove the hydrocarbon impact or the fluid impact. I would use PE, I would use gamma ray. If I have spectral gamma ray, I'll use that. If I've got ECS logs, I might use those. For mechanical properties, you might want to use full waveform sonic. You can use that for lithology too, but to me, it makes sense to pull in the density and the gamma ray and other logs, excuse me, to work with lithology. For looking at texture, grain size distribution, perhaps even porosity, this is where we might want to use NMR data or resistivity image logs, borehole image data. If we want to start looking at modeling permeability or cap pressure, resistivity ratios can come into play, or resistivity array data can really be helpful here. And I think you can see where we're going with this. Now, I've talked here about raw logs, but you're not limited to just raw logs. You can do what we call synthetic clustering. So you can take logs, you basically take electrofacies models built with these other logs and use them to build sort of a synthetic model, basically. So for instance, there's a workflow that I've done on unconventionals where I build a mineral model and then I build a mechanical model. I have those two facies models, and then I combine them to get a mineral mechanical electrofacies model. So you can definitely do things like that. This is where, for me, the power of Facimage really comes through, because you're not just limited to the raw data. You can use other electrofacies models, or you can use analytical results like your deterministic workflow results. Let's say you use a sand silt clay workflow or multimin. You can use input from those workflows as inputs for your Facimage model as well. Okay, so I think that kind of gives you an overview of how to go about defining your objectives. The key thing is, what is it you're trying to model? Is it something around lithology or mineralogy? Is it something around porosity? Is it something around your fluids? That's going to really dictate what the logs are that you're going to choose as your inputs. So just keep that in mind. So from here, what I want to do is actually jump into a demo. So I'm going to get out of the slideshow mode here. And you'll see that I've got geolog open, and I'm just going to go ahead and launch well. And from here, I'm just going to open up a workspace. And what you're going to see with this workspace here is that I've got a correlation panel up. I'm going to move my files tab so we can actually see more of the ranges here. And I've got 5 wells open: Atlas, Botine, Capella, Nash, and Vega. And you'll see I'm limiting my view from the Mount Thorley to the Branxton. I'm going to close this processing tab because we don't really need it here. And by doing that, we actually get a little bit more bang for our buck on our correlation panel here. And just to kind of set the stage, the Mount Thorley is right up here at the top. And in the lower part of the Mount Thorley, we often have gas shows. Sometimes we'll get them in the middle or upper part of the Mount Thorley, but more often in the lower Mount Thorley. That sits on top of a regional shale called the Burnham Wood that you can see coming in through here. And just below the Burnham Wood, we've got a very thin sandstone called the Archer Field. And below the Archer Field, we've got the Mulbring Siltstone. And you might be able to see here in the Botine well, and you'll see it a little bit in the Capella as well, that we have a series of finding upward sequences with the Mulbring Siltstone. And I can zoom in a little bit just to make those pop a little bit more. You can see these finding upward sequences here. That's pretty indicative of the Mulbring within the field here. Below the Mulbring is the Marie, and the Marie is a sandstone that typically has a pretty significant bit of crossover here. So just looking at this, we have a visual idea of what our reservoir, where our reservoirs might occur. But what we want to do is just a quick rock classification using Facimage. So what we're going to do is I'm going to come here with my text view. We're going to use the Atlas well. I consider the Atlas well my type well in this instance. And for the purposes of this particular presentation, what I'm going to do is I'm going to stick to raw wireline logs here. I'm going to select gamma ray. I'll select density. Instead of neutron, I'm going to select neutron density separation so that I'm removing the impact that my fluids might have on things, and then I'm going to select the PE log. So I've got those 4 logs. I'll come here and I'm just going to bring up a new Facimage window. So we're already populated with these guys here, and I just need to set my scale for the neutron density separation log, and we're ready to sort of continue on. The options tab just gives me some options for how my Facimage window is going to look. I'm not really worried about that. What I'm going to do is I'm going to come to the training data tab. This is where things really start to take off for us with regards to the model. So at this point, recall, I want to use my Atlas well as my type well. So I'm going to make sure I just have my Atlas well selected. I've got the Mount Thorley through the Branxton selected. And I'm going to select Add. Okay, and you'll notice I get a histogram for each of these input logs that I have here. And I can go to my cross plots tab here, and I can see I've got a cross plot matrix with a histogram right down the middle. And these are interactive. So if I wanted to take a closer look, for instance, at my gamma ray versus neutron density separation, I can just double click, and that will bring up this particular cross plot here. We'll take a look at this in more detail later in the workflow when we actually have a model and we can highlight the different facies. I mentioned before that what we end up doing is basically creating a composite well that basically pulls in all of our different data together. Here you'll notice I'm just working with the Atlas well. If I had pulled in data with these other wells here, you would see them added down here. But you'll notice that this Facimage well came up. It's got an asterisk by it. It is a temporary well. So basically it's only open when we have the Facimage model open. And if we were to take a look at it in text view, and go to, you'll see we have one set here. If I go to that set, you'll see that it's got depth, and then we've got gamma ray, density, neutron density separation, PE, a source reference, source well, and a tag. Okay, so if we go to the log values, what this is all telling us that the depth reference in this doesn't really mean too much. Basically, we're just taking all of the data from all of the wells that we're using to build the model and building a composite well that contains everything from top to bottom, basically. Okay, so that's what this Facimage well is. And you'll notice we know what well things are coming from. We know what interval things are coming from. It's just a way for us to keep track of what's going into the model. Okay. So at this point, there's the normalization tab. And here you have options of Euclidean, variance, and Mahalanobis. I tend to stick with Euclidean. It works pretty well for log data. For me, variance, figuring, the distance over time or how things change over time. To me, that just doesn't, it's not the best description of it. For me, variance, I see it more applicable to reservoir modeling, what's happening as we move away from the wells. But for working with log data, I think Euclidean works pretty well. And I'm going to normalize using data range. You'll notice I can use plot limits, and that's based off of the limits that I set when I first defined my model. But if you've cleaned your data, you should just be able to say data range. And you'll notice we can also use standard deviation or histogram, but I'm going to stick with data range here. And then we'll go to the models tab. And you'll see here we've got MRGC, dynamic clustering, ascendant hierarchical clustering, self-organizing map. And then you'll see artificial neural network. This is primarily for log prediction. I don't usually use this one. I usually use KNN log prediction if I'm going to do log prediction. And then you'll notice we've got STM, and that is similarity threshold method. This allows you to determine whether a model you have is going to be applicable for new data that you're bringing into your field. That's, for me, generally, that's one way to use it. Another way to use it, this is how I use it quite often, is to evaluate how it's a, I guess I use it as a QC tool. How good are the logs that I'm using to build a model? Which combination of logs is going to give me perhaps the best results moving forward for my facies model? So we're going to start with MRGC, and we're going to work primarily with MRGC here. And what I'm going to show you here is I'm going to select, I'm going to come in here, I'm going to select MRGC, and I want to set my number of facies. And I'm going to say, you know what, I want you to see if you get down to as few as 4 facies. And I want you to split it out over 35 facies, and let's see if you can give me 20 models. And this initial neurons for course-defined self-organizing map, basically think of it as this is the course-defined self-organizing map is what I think allows gives MRGC its robustness, basically. And I'll talk about how it comes into play here in a second. So we'll go ahead and say OK. So it's going to do the neighboring index, and then it does the course-defined self-organizing map ordering. And what we get, you'll notice we have, I said try and find as few as 4 facies. It got down to 5. And try and find as many as 35 facies. And it actually hit that 35 facies, but it did it in 10 models. Okay, so you can see here we get a histogram of our different facies here. Sorry, not a histogram, cross-plot matrix with a histogram down the middle. This clusters tab gives us an idea of how many data points are in each of the clusters. And this is, you'll notice I mentioned earlier that we're going to get clusters that have very different sizes, different data densities, and this is what I'm talking about. So if I go to my 35 cluster model, you'll notice I've got some clusters that have as few as 10 points, but I have some that have 228 points, right? So that's part of what I mean for that, differences in data density. So you can get the weight for each of these, and you can get the mean value for each of your input logs for these guys as well. Okay. So if we go to the facies tab, what we get here are individual histograms for the input logs. So you'll see gamma ray, density, neutron density separation, and PE. And that course-defined self-organizing map really becomes, that organizing course-defined self-organizing map really becomes obvious here. You can see here, we start off with facies number 1, and we go up to facies number 7. And you'll notice here that our facies number 1 has a higher gamma ray value. We have lower gamma ray value as we come up to facies number 7. So this suggests that we're getting cleaner. We're getting sandier as we step through these different facies. If we go to, say, the 12 cluster model, you can see that here as well. And then the 15 cluster model, you can see that distribution of our facies here. Okay. So if I were to do something, say, if I were to do dynamic clustering, and let's do 7 here. I get 7 clusters here, and you'll notice that these are not ordered at all. All right. I can come in here and order them myself. Sure. I can say, I can certainly move these guys up so that my higher values are, up towards the top and so on, but that's something that takes time. Whereas with my MRGC models, this guy, it's done for me. Okay, so that's one of the key differences between MRGC and these other modeling techniques. Okay, we have a comparison tab. And the comparison tab here allows us to evaluate one model against another model. And what we can see here, so this one, I'm looking at my 7 cluster model against my 5 cluster model. And we can see, which of my 7 cluster facies best matches which of my 5 cluster model facies. And we can see where things are split. For instance, the 5 cluster model facies 2 now becomes facies 2 and facies 4 for the 7 cluster model, whereas facies 5 in that 5 cluster model becomes 6 and 7, right? That's one way you can use this. There's other ways you can use it if you use an associated log, like a lithology log or something like that. We don't use supervised models within MRGC, and that's a topic for another conversation. But if you want to see how this works with associated logs, we can certainly do that offline. What I want to do now, though, is I actually want to propagate the 7 cluster model to these other wells. But before I do that, I do want to take just a little bit of time, changing some of these colors. It gets a little bit muddled here, so I want to change facies number 5. I want to make that guy yellow. I'm going to change facies 1 to a darker blue. I'll make this guy a little bit more of a steel blue, and we'll make this guy a cyan there. And then I'm going to make this green more of a sea green there. Okay. All right. So that's completely optional. You don't need to do that. But for me, the default colors get a little bit muddled. So I just want things to kind of stand out a little bit more. Okay. And so what I'm going to do now is I'm going to come to the propagation tab, and I'm going to select that 7 cluster model. I'm going to make sure I select all of my wells. And I'm going to double click on the parameters key. I can output a file name, the number of nearest neighbors, and most probable affected log. If I want to do any kind of smoothing, I would change the number of nearest neighbors to something greater than 1. For what I'm doing, I usually default these to 1. I'm going to define my output set name to MRGC. Often I would give a name that's descriptive of the logs that were used, so maybe nuke DT or something like that, except I didn't use sonic, nuclear logs or something like that. But for now, MRGC is fine. If I come to the MRGC tab, I can select advanced output. And if I were to say yes to this, you'll notice here that I can output that KRI, that kernel relative index, as well as my neighboring index. We also have a normalized neighboring index as well. So we can output those logs in addition to my electrofacies log, that's the number log, the color log, and the name log here. And so here, we're just going to go ahead and say OK. And I'm going to say propagate. So now we've propagated this model to all of our wells. I've got a layout here. I can bring this guy up. What this is going to show me is all of my input logs here, scaled appropriately. And now I have my electrofacies log here too. So I can go to a 1 to 1,000 scale. All right, and we can start to see some things here. So what I want to do is I'll take this guy. I'm going to copy him. I'm going to come back to this correlation panel that we had. And what I'll do is I'll just paste this guy in. And you'll see just like that, if I get rid of this appearance panel here, we actually can see now that I've pasted that guy in. I'm looking at that same correlation panel that I started off with. And one of the other things that I like to do is, let me get rid of the ghost here, is I like to color my gamma ray on the other side here once the properties box comes up. I like to color my gamma ray using the color log. So let me find MRGC. Oops, user error. Try that again. I need to select the left limit. And so there we go. So when I do that, a couple of things happen. So the Burnham wood really stands out. If you remember, the bluer colors, the cooler colors were indicative of shale. The warmer colors were indicative of cleaner gamma ray, which would it be indicative of perhaps sands. And the Mount Thorley, if we zoom in a little bit, let's take a look at this, the Atlas well and the Botine well. So that Mount Thorley, that's one of our key zones. You'll notice where we've got that crossover, we've got this red facies here. If I come down, we've got the Archer field. You'll see that red shows up again. And if I scroll down and we get to the Marie, Well, interestingly enough, with the Marie, we get some of the red, but we get orange as well. So what I can start doing here is making some calls on what the best reservoir rock might be, or the best rock types might be. And so if we come back to the Facimage model and look at this guy, this facies 6 and facies 7, well, these guys are probably going to be our best reservoir rocks, so our best rock types. Some of the other things we can do with this, if I come to the model tab, you'll see here I've got my different cross-plot matrix here. I can pull up, for instance, my gamma ray versus density here, or gamma ray versus neutron density separation, either one. And if I'm going to split my screen here, and where this actually kind of gets to be quite useful here is if I come here and turn on the highlighting option, I can see those different clusters here. So I went to the correlation panel to show you, the end result here. I probably should have stopped here first when I was talking about those different data densities here. So if we go through, what you're going to notice is with the 7 cluster model, these different facies are all about the same weight, between 200 and 400, almost 500 data points. But what you're going to notice is that they're not necessarily evenly spaced on this cross plot here. So you can see these little gray dots, those are the barycenters, or the nodes of each of those facies. And you'll notice that these are not necessarily so evenly spaced. Okay, so that for me is actually quite cool, because when I'm going through and interpreting these facies visually and manually, often what I find is that they're not going to be evenly spaced, because we're working with subsurface systems and things are not necessarily regular there with subsurface systems. There's irregularity, I guess. So for me, when I look at these guys, I look at this facies 6 and facies 7, where it is in terms of my density, in terms of my gamma ray, I'm pretty happy with that. If I look at facies 1 and these cooler facies, which are my shalier facies, or more clay-rich facies, that makes sense to me. And then we have these two sort of intermediate facies here, and I'm good with this. I like it. If I were to come into, say, this 35 facies model, you could see all of the different nodes for all of these different facies. And one of the things I could do is as I come in here is I could say, I've got this facies right here, and he's touching this facies right here. So I could select those, and maybe I want to merge them. So those two facies end up getting merged. Then I've got this facies right next to this facies. Well, where are those two facies? Well, those guys are up here. They're not right next to each other on the distribution here, which is actually quite interesting. But I can merge these guys as well. So this is, looking at these different models, you'll notice we've got, this Corsian model that I actually propagated. We have this higher resolution model where I can come in and actually start making some judgment calls and merging things together. Maybe I'm a splitter, but what I want to do is maybe I'm trying to look for something like a stringer, like a church stringer or something like that, that's otherwise hard to see, but maybe this type of resolution will help it stand out a little bit more, and I can merge these other logs or something like that. That's an example of things that I've done with clients in the past. Okay, and so when we go through this here, I think the last thing that I want to do is I want to come back to this particular guy here. You'll notice that I was able to copy this layout and easily paste it onto the correlation panel, and we can actually see everything in the correlation panel. It's just a really good visual cue for me to see, to see these different rock types, see my best reservoir quality rock, which is going to be the red rock, as well as the orange rock. So I can take this model now and propagate it to other wells within this project, and that good quality rock will stand out for me really, really quite well. One of the other things we can do with Facimage and rock typing, here we've been working with wireline data. One of the other things that we can do with it, and this is really important to kind of keep in mind, is we can also work with array data, specifically NMR data. So here we've got this well where I've got NMR data. You'll see here I've done some work on this well already. I've got my T2 distributions calculated. What I can do though, and what I've done here, is use that T2 distribution and basically built a model around it. Now I'm just going to come here and propagate this 10 cluster model here. So I'll go ahead and propagate this guy. And if I come back to here, you'll see that facies model is now propagated. And what you'll see is where I've got the sort of bigger pore sizes, I get these blue, the blue or cooler classes are indicative in this instance of my larger pore spaces, or yeah, I would say just my larger pore spaces in this instance. So I think that's also one of the strengths with MRGC, is it very easily and very quickly works with array data. We can also do log prediction as well. So you'll see here, I actually wanted to predict, I'm building a model using gamma ray sonic density neutron. And what I want to predict is, porosity, perm, and my grain density here. And so I've gone through and built models. We have this best predictors tab that will give us an idea of each of our predicted logs, what combination of logs will be best for that particular log we want to predict. And you'll notice that for porosity and perm, it's basically the same combination of logs, which is gamma ray, sonic, and neutron. But for grain density, it's just density, which makes sense. But what I can do at this point here is I can go ahead and propagate this guy out. And what I'm doing is I'm propagating out those predicted core values here. And we can come up here, actually down here. So you can see in red is the predicted core. In blue is my actual core data here. And you can see we get a pretty good match where we have core. You can see another area where we've got core. So that gives me a bit of confidence that when we move away from that area, that I've got decent core prediction away from where I have that input data. So that's just another way we can use it beyond the simple rock typing tool workflow that I showed you with the 5 wells previously. We can do rock typing with NMR data as well, and then we can do that core prediction here as well, just to give us more data to work with when we have limited data sets. Okay, I think with that, I want to come back to the PowerPoint presentation here and just wrap up here. I'm hoping what I showed you is that Facimage allows for, gives users an easy, quick, and very accurate way to go through a rock type classification using machine learning and focusing on log responses. It also enables the data to really speak for itself, especially if you leverage the MRGC workflow or the MRGC model with its course-defined self-organizing map, because what that's going to give is an impartial and unbiased electrofacies classification. I hope you found this useful, and please don't hesitate to reach out if you have questions.